Okay, sorry. I'm going to begin by recapping. So I'm going to go quickly, because some of these things I'm about to write down you've seen a lot. So let's recap. So E is our elliptic curve. NE is the conductor. P is, for simplicity, a prime of good reduction, so it doesn't divide the conductor, and even ordinary reduction. And so if T is the p-adic Tate module of the elliptic curve, then ordinary reduction means in particular that there was this filtration of T, which I was writing this way. So this is a GQP filtration. To remind you of some notation. T plus and T minus were pre-ZP modules of rank 1, and there was a particular action of the local Galois group on it. In particular, the action on T minus is unramified, and the arithmetic Frobenius acts as the unit root, acts by multiplication by the unit root of the polynomial x squared minus apx plus p. Okay, so just so we're all on the same page. W is the P divisible group, which is just T tensor QP mod ZP. And if we had a finite character chi of the Galois group of Q into, well, say into QP bar cross, but since it's finite, there'll be some ring of integers as some finite extension of QP that contains the values of chi. I was calling that O chi. And so then W of chi, or twisted by chi, was W tensor O chi over ZP with the action, the action on the P divisible group twisted by the action of chi. Right. And so then we defined a Selmer group for E and the character chi as a particular subgroup of H1Q of W chi, and it was defined by local conditions. So the classes in the cohomology group are supposed to satisfy certain local conditions. The restriction at a prime L, different from P, was just very easy condition to write down. The restriction just needed to be trivial. So this is for L not equal to P, and at P, the restriction P of the class belonged to the image of the thing coming from W plus of chi, and there's a divisible. That's obviously very imprecise way of writing it, but you get the idea. Okay. Just in case So what did we do yesterday? So we also looked at an Iwasawa theoretic picture. So we have our ZP extension of QP. So this is isomorphic to ZP. The isomorphism comes by picking some topological generator, of course, and it goes to 1. So then we have the associated Iwasawa algebra. And that choice of the topological generator also identifies this with a power series ring in one variable. So very precisely, gamma goes to 1 plus t. And then lambda star was the Pontryagin dual. So this is the continuous homomorphisms from this compact module into QP mod ZP. And there's a canonical character, psi, which is just the projection from the absolute Galois group of Q onto gamma, and then thinking of gamma as belonging to the units in lambda cross, belonging to the units in lambda, so lambda cross. The Pontryagin dual has a natural lambda structure just from the lambda sitting right there, and we can define an action of the Galois group Q using that lambda structure, and I was using the inverse of this character. So there was this module M, which was T tensor ZP lambda star. Again, we have the action on the tape module, but then I was twisting it by the inverse character. And it had the property that if we look at M extend scalars, so I think I may have missed including this on some one of the formulas yesterday, and it confused people. So if I look at M extend scalars from ZP to O chi, then I can look at the subgroup module where gamma is acting by chi of gamma. So in other words, the multiplication by gamma minus chi of gamma is 0, so I'm looking at the torsion there. Then that's naturally identified with W twisted, well, by chi inverse because of this inverse of this character. And I think I left off the inverse in one of yesterday's formulas too. So that corrects some of the things that were confusing. Okay, so that's a very quick reminder of notation. And then we had this large Selmer group contained inside the H1Q of this very big discrete group. And sort of the perspective I was taking is that this formula here is suggesting that this module M is really packaging together all of these Galois representations, these twists of our tape module by finite order characters. And also this Selmer group comes very close to doing the same thing. So it's a subgroup in here. It's very similar local conditions. The restrictions at the prime L's different from P. You can have B0 can also be the unramified condition. It's actually equivalent. So it's for L not equal to P. And the restriction at P of C actually maps to 0 in H1 IP, the inertia group at P, of M minus. That was the condition that I was imposing there. There's a reason why you work with the inertia group and instead of just the full decomposition group in terms of making certain control theorems nicer. What are those control theorems? So the point was that under a simplifying assumption that there are actually no rational points of order P, so G fixed points there, then one can show that if we take, how do I want to write this? So if we take S, and again, to talk about finite order characters, we have to extend constants from ZP to O chi. And if we look at the submodule where gamma is acting by chi of gamma, then inside here we have the Selmer group of E chi inverse. So you can sort of start to see, okay, so it looked maybe a little funny to have psi inverse here. If I had put psi, then I would have had to put chi inverses here. So I can't get away from writing chi inverses. So you have to choose where you're going to write the inverse. Anyway, so this is sitting inside here with in fact finite index, and I sort of sketched how you can even decide what this index is. So this this assumption that it's not 0 actually helps us identify this as a subgroup. Otherwise, it can be a subgroup up to some finite kernel. The finite index comes from more trying to understand the co-kernel. So we have a co-kernel, and the co-kernel is product over the primes that divide the conductor, the primes of bad reduction. We pick up the H1 unramified part of QL of W chi inverse, and that's the order of that is the analog of the P part of the Tamagawa factors. So this would be the Tamagawa factors for the Galois representation. That's the twist of the tape module looked at curve by chi, and then there was a correction term at P. So there's some possible error here. In the case of the trivial character, we analyzed the order of this. At least we could see that it was ZP mod this AP minus 1. Remember, or alpha P. Alpha P was the unit root of the polynomial x squared minus APX. plus p. So we got the order of that squared. In the case of the trivial character, when chi is trivial. And when chi is not trivial, actually the order of that group is just 1 under the hypothesis we made. So there's only this sort of funny correction term in the case of the trivial character. All right, so that's recapping the last 2 lectures. Well, not quite a recap, because once we had this formula like this, I made a few comments. If in fact the Selmer group of E twisted by the character was finite, then this is an exact sequence. In particular, this was rejected by claim. They didn't actually explain it. And then we use a little bit about the structure theory, right, of Iwasawa modules. So we have X, maybe, which is the Pontryagin dual of S, and I explained that this is a finitely generated lambda module. And we could say if torsion, so if X is torsion, then from the considerations, then we have a characteristic ideal, C of X, is the characteristic ideal in lambda, and that's generated maybe by, well, it is generated by a polynomial or a power series. I mean, you can take a generator. And then the Iwasawa theory allowed us to say that we could recapture the order of the middle piece of this exact sequence from the characteristic polynomial. So we can write it this way. Let's see. So again, if I want to deal with general characters, I have to always worry about extending to a ring where those characters are defined. So if we look at that and we mod out by gamma minus chi of gamma times the same thing, then the order of this under these hypotheses actually becomes is the order of this middle term. There's no need for hypotheses there. That's just duality, but what we can then use under the hypothesis of simplifying hypothesis of no rational p torsion and X being torsion, then in fact we can realize it as the product of the sizes of the other 2 pieces of this now exact sequence, so that this is the order of the Selmer group of the chi inverse times the order of the product over the primes dividing the connector of the orders of these H1 URs, these Tamagawa factors, and then times some correction term at the prime p, which is trivial if chi is not, trivial being 1, if chi is not equal to 1, and if chi is 1, then it's given by this. So this term, this last expression, this is exactly a kind of expression that comes out of the Bloch-Kato conjectures for special values of L functions. This is up to, ignoring maybe this correction term at p. This is what one would expect from the Bloch-Kato to be L. So the twisted L function of E, twisted by the character chi inverse, evaluated central critical value, normalized by a period, and one expects that these are to be closely connected. That this should be giving me roughly the p part of this number, the special value. In particular, when chi is trivial, we recognize this as what's predicted by the Bert-Swinnerton-Dyer formula. With the understanding that if this is infinite, then this is supposed to be 0, so infinity and 0. So I mean, really what one should think of is that this is taking values in O chi, this ratio, and the size of the index of the ideal generated by this should be given by the size of this. So, And so this kind of, but at the same time, at the same time, the Iwasawa theory tells us that this order of x, well, maybe the order of x tensor O chi modulo the gamma minus chi of gamma of x tensor O chi, tensoring over Cp, of course, that this is also given as the order of lambda, to extend scalars up to O chi, of gamma minus chi of gamma, that ideal, and the generator of our modulo, the generator of our characteristic ideal, and gamma minus chi of gamma. And so, well, if I just mod out by that, remembering, I mean, if we think of this as power series, this is just O chi now, double brackets t, and I'm modding out by 1 plus t, so I'm modding out by t minus chi of gamma minus 1 and g of t, so I'm looking at the size of this, and this is nothing more than the size of O chi modulo g evaluated at chi of gamma minus 1. So then the value of, or at least the size of the p-adic valuation, or the index inside O chi, of the value of this generator of the characteristic ideal at a root of unity minus 1 is supposed to give me the value of this sort of Bloch-Kato formula. So it's supposed to be closely related to an L value. And so in the best possible world, you could pick G such that G evaluated at chi of gamma minus 1 should just be chosen so that it is just maybe that, which is, if you could, then this would be, I mean, there's really no other possibility, right? You have to be able to do this because we believe all of these conjectures. So you can start maybe by asking the question, does such a G exist? Not even as a generator, just as an element of lambda. And that's the sort of analytic side of Iwasawa theory. So I've been focusing on the algebra, the definition of Selmer groups, the properties of these Selmer groups and the like, but there's also an analytic side to Iwasawa theory, which is the p-adic L functions. So this gives me a reason now to introduce a p-adic L function.
What was the definition of omega E again?
It's a Néron period for the elliptic curve. You have to be careful with the periods. I'm going to actually, right. This connection, that's something you would put into quotes, and this is something this equality I would put into quotes for the moment to make things more precise. And now I'm going to be more precise. So we want a p-adic L function for E. So we want an element in G, or an element like G. We want something in lambda that has an interpolation property very close to this. That's what our sort of analysis of the Selmer group suggests we should see. So, and you can go looking for it. Actually, it was probably, I'm not sure which came first, but certainly p-adic L function for E has been known for a while, maybe going back at least to work of Mazur and Swinnerton-Dyer. Back in the dark ages, when you actually had to sort of make a distinction between the elliptic curves that were modular and the elliptic curves that might not be modular. Fortunately for us, we entered the age of enlightenment, and we know that elliptic curves over Q at least are modular. So let me describe the p-adic L function of E. So it's actually, so if we have E, and there's an associated to E, there's a modular form, F, an eigenform, sum equals n equals 1 to infinity, A of n, Q to the n. And of course, AP for any prime P is the AP of the elliptic curve. This is a weight 2 new form of level given by the conductor of the elliptic curve. And it has the property that the L function of the elliptic curve is just the L function of the eigenform. In fact, the L function is only attached to an isogeny class of an elliptic curves. So for each isogeny class of elliptic curves, there's this new form. And of course, this is due to Wiles and all. This is particularly important because the Dirichlet series or Euler product defining the L function of the elliptic curve only converges absolutely for real part of S larger than 3/2, whereas we have analytic continuation for L functions of cusp forms, and so we can talk about the value at S equals 1. And of course, L of chi of S is just going to be, any twist is just going to be the twisted L function of the modular form. Associated to f of e, you can associate very naturally up to, at least up to a p-adic unit, some what we might call canonical periods. And there's actually two of them. Omega f of e, plus and minus. So there's two canonical periods that can be defined using sort of de Rham cohomology. So you can think of f giving rise to differentials, maybe 2 pi if of tau d tau if you're thinking of pulling back to the complex plane, and then you might so then use the de Rham comparison theorem between de Rham cohomology and Betty cohomology to sort of define some periods from using that differential and its complex conjugate. Anyway, so there's a very natural construction, and you choose this period so to normalize things so that you're in the integral homology, or at least the p-adic integral homology, or cohomology. And so that at least defines the periods for f of e up to p-adic unit. So they're fairly canonical. And then the problem is to compare that to the de Rham period of the elliptic curve, at least in the case, or in the Rome period of the elliptic curve, at least in the case where the residual representation is irreducible, where E P is there's no rational p torsion, then, and under a few other mild hypotheses, then we can show, in fact, that those periods, the Rome period of the elliptic curve and the omega Fe plus, are the same up to p-adic unit. So I'm going to talk about, I'm going to write things in terms of the periods of omega of f of e, but it's going to be the same as omega of e. Okay, so then constructions of Amis, Vilu, and Wischek, and then later explained by Maser, Tate, and Teitelbaum, produce for us, in fact, a p-adic L function. What's the p-adic L function interpolating? Well, one of the properties of these periods is that, in fact, if I take Lf of e and I take chi, and I look at L of chi 1, and I'm going to take chi to be an even Dirichlet character. So chi of as a Dirichlet character, chi of minus 1 is plus 1. This in general will be a transcendental number, and the point is that when I normalize by these periods, in this case it would be just the plus period, and if I had odd characters I would use the minus period, that this is algebraic. And the point of the sort of p-adic L function is actually to show that these behave nicely p-adically. They're sort of interpolated by a p-adic analytic function. So there exists a function L, maybe LP of E, probably I call it something like this in the notes, in lambda, which satisfies a certain property that shows that it interpolates values of this type, such that so if we take one of our finite order characters, QP bar, Frost, and so finite order, and again I'm going to use this abusive notation to think of this as a Galois character by projecting onto GQ onto gamma and then identifying through class field theory with a Dirichlet character. And I haven't told you what conventions I'm using for class field theory, so you have to figure that out for yourself, because I'll get confused. So it has the problem. So if you have such a homomorphism, I should note, maybe parenthetically, that if you have such a character, then I can extend it from a character of gamma to a homomorphism of lambda into QP bar. So this gives rise to phi of k, which is a homomorphism from lambda into QP. So this is a ring homomorphism on restricted to gamma is just the character chi. So you just extend linearly, and then it has the property that for such the image now of phi chi of L under such an element. Well, I can compare that with my L values. My L values are algebraic, so they belong to Q bar, and I'm thinking of Q bar as being inside QP bar. In fact, I probably fixed such an embedding when I wanted to talk about decomposition groups, even things like that. So this is, in fact, LFV of chi inverse of 1 over omega of f of E plus. Note that characters of gamma are going to all be even Dirichlet characters. So it's not quite an equality on the nose. There's a correction term or an interpolation factor that has to go in there. And let's see if I can get this interpolation factor correct. So chi of gamma is going to be a p power root of unity. I'm going to write that as zeta p to the t to mean that it's a primitive p to the tth root of unity. So t is going to be greater than or equal to 1 or 0. And so, because the formula is going to depend on that t. So there'll be two cases. There'll be and when the t is 0, so with a trivial character, it looks like, do I have a cheat sheet? I have a cheat, yes, okay. So I have alpha p minus 1, 1 minus 1 over alpha p. Well, in the case of that we're dealing with good reduction, so we get squared. Well, that should actually, alpha p is a unit, so the valuation of this is the same as alpha p minus 1. So that's looking like the valuation of that correction term we had in the in our comparison between the Selmer group of finite level and the Iwasawa Selmer group. That's when so it's this when chi is trivial, and it's alpha p to the minus t plus 1, and then there's a p to the t plus 1 divided by the Gauss sum for chi inverse when chi is not trivial. And I should point out that when gamma of chi has, when it's a primitive p to the t through unity, the conductor of the character as a Dirichlet character is p to the t plus 1. So that's where you're getting this p to the t plus 1. So that's the conductor of the character chi, and so the Gauss sum is absolute value p to the t plus 1 over 2. Okay. So this is the p-adic L function of the elliptic curve. Where does this come from? There's two constructions. This is not some categorical thing. I don't know why I wrote the hyphen there. This is not a two construction. There's two constructions. So the first comes, which is the construction of Amisvilu and Vishik and of Maser-Tate and Teitelbaum, which comes through modular symbols. So as I said, you have these differentials in the cohomology of the modular curve coming from your cusp form, and you've normalized them to be integral, or at least p-adically integral. and then you can evaluate them on certain elements in the homology, or maybe relative homology. You might worry about the cusps in particular. The classical formulas, like from 0 to I infinity of f of y. I guess I should just write 0 to infinity f of I y to the minus s dy over y, or something like this. Being I'm not getting this quite right? But it looks something like this. You can think of this as pairing your differential, or integrating your differential for f z dz along a path from 0 to infinity, so between two cusps on the modular curve. And that's in fact, so once you've normalized this differential to be integral, the other side will also be integral or algebraic. That's how you prove this algebraicity, and with more care, you can show, at least for these ordinary modular forms, that you can construct sort of a p-adic measure that interpolates these. And then there's sort of a dictionary between p-adic measures and elements of lambda. Very, very precise. Oh, right. So there's an S there. Yeah. And so when you take S as 1, then these go away, and that's some special part of the f z dz differential. All right. There's a second and very important construction that comes from Rankin-Selberg constructions. We've heard about Rankin-Selberg objects before. So this is, in this case, you would take a Peterson inner product between f and a product of two Eisenstein series with various characters. I'm being very sketchy. And this Peterson inner product then unfolds to a product of L functions, maybe LF chi, like 1, chi 1, 1, and LF times LF chi 2, 1. These characters, chi 1 and chi 2, depend on the characters of the Eisenstein series. I'm thinking of both, maybe in this case of the Eisenstein series, both having weight 1 or something like this. And you can vary the Eisenstein series in p-adic families. We saw that very explicitly in one of Romjar's talks yesterday. And so then, you can interpret this Peterson inner product as sort of as applying some linear functional to the space of p-adically varying modular forms. So this can also be turned into a p-adic measure. And what you have to do, but you're getting a product of two L values, and so you have to sort of get rid of one. And it's in fact possible to show that you can arrange things so that this character chi 2 is such that this L value, really you'll get omega F plus maybe an omega F minus. You can always make this a p-adic unit. And so you can, that becomes sort of an innocuous, you can even keep it constant and only vary the character chi 1. So this gives an additional construction. And it's important to have both constructions. In fact, it's this second construction that shows up, for example, in the work of Kato, when he realizes certain things as interpolating the p-adic L function or connected to the p-adic L function through Rankin-Selberg expressions for the p-adic L function. So in the world, the p-adic L functions and their constructions is sort of also a big subset of Iwasawa theory, and not represented at this conference. But and you often have multiple constructions of what seem to be the same p-adic L function, but your periods come from different things, and here they might come from the homology of the curve, or they're coming from Peterson inner products, and you have to worry about comparing periods. And in fact, most of special value, the theory of special values, you can think of as really just comparing different periods. All right. Anyway, so we have this p-adic L function, which has exactly the properties that we want of a generator for the characteristic ideal of the Iwasawa-Selmer group. And so the statement of the main conjecture for Iwasawa theory, or at least the cyclotomic main conjecture for the elliptic curve, is now going to be completely anticlimactic. So the main conjecture. But maybe it deserves a fresh pen. And I'm emphasizing that it's E over Q infinity, because in fact there's a whole zoo of main conjectures, and I hope to get to that. So here we have it, the main conjecture for E over Q infinity. Right, so the first part is going to be that x, which is our x of E over Q infinity, we're going to conjecture that it's a torsion lambda module. And if it's a torsion lambda module, then all those sort of interpolation properties for it hold. It's in fact, because as I explained, and I left as an interesting exercise. If it's torsion, then in fact there has no pseudonal submodules, and so all of the interpolation that we would like works really well. And so we expect, in fact, the characteristic ideal to look like something like L, and so that's the next part of the conjecture. So that the C of X is actually generated by the p-adic L function. Maybe, yeah, I'll leave it like that. So the C of X is generated by this p-adic L function, L. Now, going back to some comments I made about periods, so here I'm defining my p-adic L function with the period for the new form that's associated to the isogeny class of the elliptic curve. If you wanted to use the, actually, yeah, so this isn't done. All right, so if I wanted to relate this to what I had written down before, the numerator here is LE of chi inverse 1. This may not be omega of E, and it will be omega V up to some power of P, but that could even be a negative power of P. So I'm gonna play it safe, and I'm gonna say this equality should at least hold in lambda tensor QP. So I might have to invert P, and even in lambda if E under this hypothesis that I was making before, that there's no rational torsion. The Galois representation is, well, maybe I should actually, even in here, this is true. Am I happy with that? I'm gonna put it this way. If E of P is irreducible, I'm happier with this GQ representation. Sorry about that. And things can get kind of interesting when E of P is not an irreducible Galois representation, and that's discussed in some detail, or at least in some cases, in a paper by Greenberg and Watzel. And you can really have situations where, particularly if you're using the period of the elliptic curve, then you're not an equality in lambda, but just in lambda tensor QP. So, but for all intents and purposes, you can think of this as being an equality in lambda. Actually, I don't care about that. All right. So that's the main conjecture. When did I start? Where's Brighton? Okay. What's that? Okay, so 9:05. Sounds good to me. So I'm gonna go to 5 more minutes or so. So this is actually there are alternate formulations of this main conjecture. This is what you might call the main conjecture for E of Q infinity with L function. And there's an important formulation without L function that ties actually a lot of what I've said into the kinds of things that David and Sarah are talking about. So there's a main conjecture without L functions. And I wanted to talk about this because I have the challenge now of writing down a 4-term exact sequence up here, and so I'm going to write an exact column. So what one has you can define. So I'm now going to look at things like T tensor lambda with the action of the Galois representation being EP tensor psi, not psi inverse. The dual of this is a nice compact Galois module, and the dual of this module, the arithmetic dual of this module, is M. And so we could also define Selmer groups for compact modules using continuous Galois cohomology, as well as Selmer groups of discrete Galois modules. So we could have defined Selmer groups for T, but actually, okay. So that's my 4-term exact sequence. I'm going to have right. Okay, so we'll have the Selmer group. Oh, I'm going to call this. I should call it like script T, but it's actually going to be bold T, or blackboard bold, even though we don't have blackboards here. So it's going to be a Selmer group for this T. So that's going to be some subgroup of the H1 cohomology of this. We're going to take classes that are unramified away from P, but no conditions at P. So I'm going to call that the relaxed Selmer group. The strict Selmer group, which is going to be STR, would be having the restrictions at P be 0, but away from P, everything is always unramified. Okay, so all right. So then I can restrict at P, and this will land in the H1 QP of T. And I'm going to look at its image when I mod out by the image of H1 QP of T plus. So T plus, as you can imagine, right, is just going to be T plus tensor lambda with the same Galois action. So, yeah, forget about that. Okay, and this by local duality is actually dual local Tate duality to the H1 well, what is it actually? It's not quite H1 QP. So I'd like to say that it's dual to the dual of this. So the Pontryagin dual of that by Tate duality. It's actually dual to the image of H1 QP of M inside there, the dual of the image. So we'd actually write this image and put the dual up there. Okay, that doesn't look so nice. Well, what lands inside that image? I'm sorry, it's dual. It's dual to the kernel. Sorry, dual to the kernel of that. Well, what lands inside that kernel, if we hadn't dualized, would be our Selmer group for our elliptic curve with the restrictions of those classes. And so when I dualize, I'm going to get a map. This is the dual of the restriction at P map, and that'll land inside the X that we had. So this was our S dual, and S maps to that kernel by restriction. And then what's the kernel of that restriction would be sort of the Selmer group that's strict at P, that the restrictions of the classes at P are 0, and the dual of that I'll call X strict. So this would be the dual of the S strict dual. And so we have this. And this is actually an exact sequence. This is a consequence of Plateau-Tate global duality, that this is an exact sequence. Now, I'm not saying that we have an injection from the relaxed into there yet. Although, if X is torsion, and under our conditions of things like this, then in fact it must be an injection. This is a rank, maybe I should even say this. This turns out to be a rank 1 lambda module under our conditions, and there's a nice homomorphism, which is often called a Coleman map, or the Bloch-Kato dual exponential map. So it identifies that with lambda. And if X were in fact known to be torsion, then this turns out to be an injection. You can show, because the kernel would have to be roughly a torsion lambda module, but there's no torsion lambda by a lambda torsion by this hypothesis. Kato constructed we'll call it Z Kato inside this restricted or relaxed cohomology for T, a lambda module. It's free and rank 1. So it's inside here. We can look at the restriction. So we can look at the restriction at P of this module locally, and then you can apply the Coleman homomorphism to this restriction. And this is exactly the thing that Kato analyzed through his explicit reciprocity map and showed, was related to the p-adic L function for E by sort of this sort of Rankin-Selberg construction of the p-adic L function. But the upshot is that this is actually the p-adic L function. So in fact, so then one can use this. So the main conjecture without L function is just stated this way, that cell relaxed of T is a rank 1 lambda module that would be consistent with this being an injection, because it would be a submodule of lambda, and that if we look at this object cell T modulo Z Kato, we can talk about the characteristic ideal. So the claim is that that's, and the claim is that since this is a free Z module of rank 1, and this is telling me, in fact, this is an important part of showing that it's a rank 1 and not just 0. So this is torsion, since it's a free Z module rank 1 inside a lambda module rank 1, and that characteristic ideal should in fact be the characteristic ideal of this strict Selmer group, or dual Selmer group. And one can show that this main conjecture, through this exact sequence, this main conjecture is actually equivalent to the other two main conjectures, or the other main conjecture, and the two main conjectures are equivalent. Are equivalent. The equivalence does require Kato's explicit reciprocity map that tells me that the image of his elements, or his lambda module under the Coleman map is the p-adic L function. And so the sort of a more detailed sketch of this equivalence is given in the notes, but this is actually a very important fact. And so in most of the progress we have beyond the classical main conjecture, improving any sort of main conjecture, we actually have to combine both the main conjecture without L functions, where progress often comes through Euler systems, with the main conjecture with L functions, where progress comes through the kind of arguments that Romeo Arifi talked about yesterday. So I'm gone a little bit over, but all right. So next two lectures, at least in the next lecture tomorrow, I will talk more about what's actually known about this main conjecture, some theorems and the ideas of the proofs, and then we'll deduce some arithmetic consequences. Thanks.
Questions? When you stated the main conjecture for elliptic curves
Yes.
is irreducibility condition.
Yes.
And I was wondering if there's something inside of the classical conjecture that makes you expect it's a natural one to look at.
Well, how would this compare to the natural one? Well, it's a little. So the natural or the classical one is for a one-dimensional character. So the issues of reducibility and irreducibility don't show up. The closest you might think of this is that for the trivial character, the p-adic zeta function has a pole, and the main conjecture is really about the denominator, or the numerator, where you've sort of gotten rid of the pole. So these sorts of having to have certain exceptional cases do come up.
Other questions? Okay, let's thank Chris again.